All right, let's talk about our computers. We click, we type, we swipe all day long. But have you ever stopped to wonder what's really going on inside that box? What's happening between your click and the magic that just appears on screen? Well, today we're going under the hood. We're going to peel back the layers of language, logic, and electricity to see how it all really works. And it really all starts with this question, right? We use our phones, our laptops. We feel like we're in charge, but are we really in the driver's seat? I think there's a much deeper level of understanding and, control that's totally within your reach. And we're gonna find it. And that's the heart of it, isn't it? This isn't just about knowing some technical trivia. It's about that incredible feeling, that satisfaction and freedom you get from truly understanding the tools you use every single day. It's about building something yourself. So, here's our roadmap. First, we'll look beyond the shiny graphics on the screen. Then, we'll dive into the different languages our computers speak, from our language to theirs. We'll unpack the massive role of the operating system, see how code actually talks to physical hardware, and then, at the end, we'll lay out a clear path for how you can achieve mastery. Okay, first stop. We have to get beyond the surface. I mean, we all know how to use a computer, right? That's the easy part. But mastering it, that means really looking under the hood. I love this analogy. Think about it. You don't need to be a mechanic to drive a car, but a top-tier NASCAR driver, they understand every single vibration, every sound the engine makes. They feel the machine. That deep knowledge lets them push it to its absolute limit. Well, it's the exact same idea with your computer. So let's peel back that first layer. We're talking about programming languages. These are the incredible bridges that let us take our very human ideas and translate them into a set of instructions a hunk of metal and silicon can actually understand and execute. At the very top, you've got high-level languages. You've heard of these: Python, Java, C++. They're designed to be readable for us humans. They use English-like words, and they let us think about big ideas without having to worry about the nitty-gritty details of the specific computer it's running on. Now, take one big step down, and you land in assembly language. Okay, now we are getting much closer to the metal. You can still see some English-like commands here, but now you're writing instructions that talk very directly to the computer's processor, the CPU, its brain. And finally, we hit bedrock. This is machine language. It is the computer's native tongue, and it's nothing but ones and zeros, pure binary. Every single program, no matter how fancy or high level it is when we write it, eventually has to be translated down into this fundamental language for the hardware to do anything at all. So you see, there's this constant trade-off. It's a balancing act between what's easy for us to write and what's fastest for the machine to run. High level is easier, more abstract. Low level gives you that raw speed and direct hands-on control of the hardware. And you know what? True mastery is knowing exactly which tool to grab for the job at hand. Okay, so we've got languages to write our instructions. But what keeps all those programs from crashing into each other? What manages everything? Well, that is the job of the operating system. It is the conductor of this entire digital orchestra. The OS is the ultimate unsung hero. Seriously. It's juggling a million things in the background that you never even think about. It's deciding which program gets to run, where to store data in memory, how to talk to your printer, how to organize your files, all while keeping things secure. It's the silent force that keeps the whole show on the road. And here's a perfect example of how these behind-the-scenes choices make a huge difference. When your computer starts up, it has to launch a ton of services. The old way, using something called init, was to start them one by one in a slow, single-file line. The modern way, with systemd, is to start a bunch of them all at the same time in parallel. And the result? Your computer boots up way faster. It's all thanks to smarter OS design. So we've seen the code, and we've met the OS that manages it. But now, for the final piece of the puzzle. How do these abstract ones and zeros actually make something happen in the real physical world? Whoa. Okay, don't worry about understanding a single word of this code. That's not the point. Just look at it. This is a real snippet from the Linux kernel. This is what it looks like when software is talking directly to a very specific piece of hardware. This right here, this is the point where the digital world literally touches the physical one. So let's put it all together. Follow me on this. 1. A programmer like you writes some code. 2. A compiler translates that into machine language, those ones and zeros. 3. The operating system loads that code up and tells the CPU to get to work. And 4. The CPU sends tiny electrical signals to the physical hardware, making your screen light up or your speakers make a sound. It's this beautiful cascade from an abstract thought all the way down to a physical action. So now that we've taken this journey to the core of the machine, You might be asking, so what? Well, the so what is that this deep knowledge, this is the foundation for building real-world skills and for gaining true technological independence. And look, this is not just an academic exercise. Understanding all these layers is the absolute bedrock for some of the most important and in-demand jobs in tech right now. People who can bridge that gap between software and hardware. People like DevOps engineers or SREs. They're incredibly valuable because they understand the whole machine from top to bottom. But how do you actually get there? Well, the answer is pretty simple, but it's not easy. You can't just read about it in a book. Mastery comes from doing. It comes from writing code, from breaking things, from fixing them, and from throwing yourself at all sorts of different real-world problems. So here's a clear path you can start on today. 1. Learn the core concepts that apply everywhere. 2. Immediately start building projects. And I mean things that actually solve a problem for you. Make it personal. And 3, and this is so important, read code written by other people, by the masters. See how they do it. Look, this journey can be frustrating at times. You are going to hit walls. But I want you to remember this quote because it captures the magic of learning this stuff perfectly. You just keep pushing and learning and trying things, and then one day, it all just clicks. The complex layers snap into place, and for a moment, everything becomes beautifully, brutally simple. That's the aha moment you're working for. So we've taken the machine apart. We've seen all the layers, from the code you type on the screen, all the way down to the electricity running through the circuits. We've put it back together. The only real question left is, now that you know how it all works, now that you know what's possible, what are you going to build?